Okay, nuclear binding energy. This is going to be the last part of lesson 34. And kind of not our most complicated math, but there is going to be some math in this section. So the nuclear binding energy is the energy that's required to break up a nucleus. So it's the same concept as bond energy when we talked about breaking bonds and how triple bonds take more energy than double bonds, which take more energy than single bonds. So it still takes up energy. It still takes energy to break up a nucleus, like hitting it with a hammer. And so when we break up a nucleus, we are breaking up into its components, which are protons and neutrons. Now, every nucleus is made up of protons and neutrons that are held together with energy. So that's the energy we're trying to overcome. When the mass of the individual particles is compared to the total mass of the nucleus, it becomes apparent that they are not identical. Plot twist. The difference is known as mass defect. So what that means is when I go and I take the, say I take elemental carbon and I weigh out 12 grams of that, but then I do the calculations based on how many protons and neutrons and electrons might be in there. If I could calculate and count all of those, it turns out that mathematically, based on what I know a proton, a neutron, and an electron weigh, I don't get the same number. And that difference between what we actually see and what we calculate, actual and theoretical, are not the same. And that's mass defect. So let's calculate the mass defect for the carbon 12 nucleus. And we're going to, because it's carbon 12, this isotope should weigh 12.00000 AMU. It is a very specific number. It's exactly 12. So let's calculate. All right. So the mass defect is going to be the sum of all the individual particles multiplied by how many there are, and then subtract that from the mass that we're given here. So in carbon 12, we're going to have 6 protons, 6 electrons because it's neutral. If it wasn't neutral, there'd be a little sign up here at the top, but there's not, so it makes it neutral. And then because it's carbon 12, we're going to have, heavens to men, there we go, 6 neutrons. All right, so let's calculate this. So I have 6 protons. Each proton weighs 1.0073 AMU. Okay, so this is going to be the protons. Now I'm going to add to that 6 times 0.00055 AMU. So remember, AMU is atomic mass units, which is also equivalent to grams per mole. And then I'm going to add to that the 6 neutrons times pretty much 1. A neutron and a proton don't have the exact same mass, but it's close enough that you're talking about 0.0015 AMU difference. And unless you're talking about a lot of neutrons and protons, it's not going to have as big of an effect as you think. Okay, so I'm going to add those all together, and then from that, I'm going to subtract the nucleus weight. Okay, so everything right here is going to be theoretical. What I have here is measured. Okay, so I'm going to take each piece one at a time. This is 6.0438 plus 0.0033 plus 6.0522. Add those together, and then I'm going to subtract 12 from that. 0.993 is what the sum of those 3 are, and make sure I don't lose a digit. Okay, which gives me a mass defect, not a very big number, which they usually are not horribly large numbers. Okay, 0.0993 AMU. Okay, that is the mass defect. Okay, so it's not hard math. Yes, you do need to know these values. Okay. If you were close, ballparky, you may not, like if you just did one, you probably wouldn't have a significantly different answer. You might be able to guess based on multiple choice which one the right answer is. Okay, so this loss in mass shows up as energy, specifically heat, given off to the surroundings. To calculate the energy, we can use Einstein's mass energy equivalence relationship, which is the famous E equals mc squared. Okay, so I think in physics you'll spend more time on this, but it's probably the most famous equation in the world is E equals mc squared. Okay, and I'll tell y'all, when my grandpa was a student at UT Austin after World War II, he saw Albert Einstein on campus and said he was the ugliest man he had ever met in his entire life. But I guess when you're smart like Einstein, you don't necessarily care so much about being good looking. All right, so calculate the binding energy for the carbon-12 nucleus, and then it asks, is the formation of the carbon-12 exothermic or endothermic? We're going to answer it, but I'm not going to expect you guys to do that because we don't typically get into that level of nuclear chemistry in this class. So to calculate the binding energy, we need a couple of things. The first thing we're going to need is E is what we don't know. C is going to be the speed of light, which you might know is either 2.998 times 10 to the 8th meters per second, which is velocity. However, sometimes that gets rounded up to 3.0 times 10 to the 8th meters per second. So that's a constant, the speed of light. The other thing we need is that energy is typically in units of kilograms, meters squared, seconds squared. And so we can't use our mass that we see up here in AMU. We have to somehow convert it to kilograms because that's the units we need here. So that conversion is for every 1 AMU. It is 1.6605 times 10 to the negative 27th kilogram. And you do not need to memorize this. This is old. This C constant we used last semester when we did light. So it's review. I would like for you, or you need to know that one. But the one in the second one, you do not need to memorize. Okay? Memorize the one in yellow. Do not memorize the one in blue. I will give it to you. Okay? So we're going to do that conversion within the problem. We're going to take our mass defect. And as long as I line up all of my units, the nice thing about this type of stuff is they're going to cancel out. I'm not creating any extra steps for myself. And because I used the full version in my notes, I'm going to go ahead and leave it this way. And make sure you don't forget to square the speed of light. Okay? So once I multiply all the way across and make sure I would square my C first, then multiply by this, then multiply by that. And we get an energy value of 1.48 times 10 to the negative 11th units of joules. Okay? Which is also the same as kilograms per meter squared, second squared. Okay, you'll learn way more about that in physics. And so this would be an exothermic reaction because the mass defect is a positive number, which makes the energy a positive number. If the mass defect was negative, the energy would come out to be negative, and that would be an endothermic reaction. You're at a deficit. Okay, so because the definition of binding energy is energy required to break up a nucleus, the binding energy is expressed as a positive number. Okay, and we've done that. So there's our final answer. In order to compare binding energies of various isotopes, it's useful to compare them to per nucleon. I'm not going to do that. It might be helpful in some cases, in some classes, but we're not going to compare them. So we're not going to worry about it. Okay, what you're more likely to see is something like this figure above, where the nuclear binding energy, so this is a really small number, This is not really, but this is a really small number, and then the one at the top is a bigger number, and it goes mass number left to right. And so the nuclear binding energy per nucleon is what we didn't calculate here. But these types of graphs, what we look for is the very top of the peak here. This is going to be the most stable, and everything to the left and the right is going to be less stable. I was almost saying like most and less at the same time. So which element based on this is the most stable when it comes to nuclear binding energy? And that's iron. Y'all probably all heard him say he just ate his cheese sandwich. So he's eating a Cadbury egg. All right, so the nuclear binding energy is the greatest for the mass number 56. But you're going to see here that these are not all that different. However, because the nuclear binding energy, and I guess I should say this, so because the nuclear binding energy is really strong with everything there in that box, especially for the radioactive ones like here and over, that means that when they break apart into something smaller and a particle, they release a lot of energy, which is what makes something like uranium a really great radioactive fuel source. And so it's not to say that these are so stable they don't break apart. This is because there's so much energy holding the nucleus together. When they do break apart, it releases a lot of energy. Okay? All right, so that is lesson 34. As far as I know, we are getting pretty close to the end of the math. We're going to have some review math, but a lot of conceptual stuff that you need to make sure you just have read through really well and that you're familiar with the different aspects. So if you are not a mathy person, you can give a little hurrah. We're getting close to the end of the math. Okay. Up next will be lesson 35, and then after that we have lesson 36 and 37.